In a universe full of amazing things, there's a huge hidden part we can never see directly. Far beyond the galaxies our telescopes can find, there is a strange line, a limit to how far we can see into space. This line marks the edge of the observable universe, the farthest light that has had time to reach us since the universe began. However, thinking about what might be beyond that far-off edge brings up big questions about space, time, and what reality really is. So what's beyond that edge? Is it just more of the same, endless stars and galaxies, or is it something totally different, something we can't even begin to understand? Before we begin this video, let us know where in the world you're watching from, and what the time is for you right now. Post it in the comments below, and settle in for a journey that will change your view on space forever. At the farthest edge of what we can observe in space lies a strange and fascinating boundary, a kind of cosmic horizon that shows us the limit of what we're able to see. Beyond this invisible edge, the universe doesn't just end, it keeps going. But no matter how hard we try, we can't see what lies beyond it, because the light from those distant places hasn't had enough time to reach us yet. This happens because the universe has been growing ever since it began. Some galaxies are racing away from us so fast that their light simply hasn't caught up. It's not that they aren't there, they are. It's just that their light hasn't arrived. So to us, they remain hidden. Think of it like standing on the shore of a giant, endless ocean. You can look out as far as your eyes, or the light can travel. The horizon seems far away, flat and quiet. But you know there's more beyond it, more waves, distant islands, and perhaps even entire continents. You just can't see them from where you stand. In the year 2023, a major study published in Nature shocked the scientific world. Information from the strong James Webb Space Telescope showed something that, based on current ideas about the universe, just shouldn't be possible. Scientists had found 6 huge galaxies that seemed to have formed only 600 million years after the Big Bang. To understand how surprising this is, remember that the universe is thought to be about 13,800,000,000 years old. But these galaxies, which are unusually big, appeared far earlier than scientists thought was possible. Based on everything we know, galaxies this large should have taken billions of years to form, not just a small part of that time. In fact, the math shows that these galaxies should be at least 10 times smaller, or even 50 times smaller, than they actually are. Why? Because there just wasn't supposed to be enough normal matter, the stuff that makes stars, planets, and life, to build such big galaxies so early in the universe's history. If these results are confirmed, they could question one of the most basic ideas in science, the age of the universe. Some scientists now think the universe might not be 13,800,000,000 years old, but instead an incredible 26,700,000,000 years old, almost twice as old as we thought. This isn't just a small change in science, it's a discovery that could change everything we know about space and time. One of the scientists who worked on the study, Erica Nelson, said that even if only one of these galaxies is real, it would push the limits of what we know about the universe. Right now, no existing scientific ideas can fully explain this strange finding. But some scientists have shared a bold idea called dark time, a theory that suggests galaxies and other cosmic structures might have formed much faster than we ever thought. If that's true, scientists would have to completely rethink how the universe grew and changed. Even though we don't fully understand the size and shape of the universe, we can guess that if it has edges, even unclear or unknown ones, it should be theoretically possible to reach them. But what would that trip be like? For hundreds of years, people have asked these same questions. Long ago, ancient people were obsessed with the idea of a center and an edge to the universe. A famous engraving from the 19th century even shows how people in the Middle Ages imagined the border of existence, beyond which lay the strange forces controlling everything. Now, when we look at the red supergiant star Betelgeuse, we're not seeing it as it is right now. We're seeing it as it was 500 years ago, because that's how long its light takes to reach Earth. In truth, Betelgeuse might have already exploded in a supernova, but we wouldn't know until that light finally gets here. Gravity works in a similar way to light when it comes to delays. We don't feel the sun's gravity right away. The pull we feel is coming from where the sun was 8 minutes and 20 seconds ago. because that's how long it takes for both sunlight and gravity to travel to Earth. So, if the sun suddenly disappeared, Earth wouldn't feel it right away. Our planet would keep orbiting as if the sun was still there for those 8 minutes and 20 seconds. Only after that would Earth and the other planets start drifting away. The same idea works with galaxies. The Andromeda Galaxy, the biggest one near us, is moving in our direction at a mind-blowing speed of about 400,000 kilometers per hour. But since we're seeing it as it was long ago, it's actually 900 light-years closer than it looks. To get a better idea, the nearest star to the Sun, Proxima Centauri, is 4 2400ths light-years away from Earth. Even with the fastest spaceships we can make today, it would take tens of thousands of years to reach it. So the fact that Andromeda is nearly 1,000 light-years closer than we thought is a huge deal. When we look deep into space, we can only see as far as light has had time to travel to us since the universe began. The farthest light we've seen comes from 46 billion light-years away. But if the universe is only 13,800,000,000 years old, how is that possible? Shouldn't we only be able to see things 13,800,000,000 light-years away? The answer is something called dark energy and the fast stretching of the universe. Light from those faraway places didn't just travel to us in a straight line. Space itself has expanded, so now we can see much farther than the age of the universe suggests. That's why we can see things 46 billion light-years away in every direction. So, even though the observable universe has a limit, the actual universe probably goes way beyond what we can see. But does it ever really end? Is there a wall somewhere? Or does space just go on forever? Let's go back to the thought experiment. What if we built a spaceship, picked a crew, and sent them flying straight ahead as fast as possible to try to find the edge of the universe? Astronomer David Kipping from Columbia University has thought a lot about this. He suggested building a spaceship that could speed up forever at 10 meters per second squared. Why choose that speed? Because at 10 meters per second squared, the people on board would feel the same pull as gravity on Earth. That means they wouldn't float. They'd feel like they were standing on solid ground. Just so you know, Earth's gravity actually pulls at 9 8/10 meters per second squared, but rounding it to 10 makes things easier. In the first second, the spaceship would be going 10 meters per second. After 2 seconds, it would be going 20 meters per second. By the end of the first hour, it would be moving at a crazy 35,280 meters per second, and it would keep speeding up. After 2.5 hours, it would fly past the Moon. In 1 week, it would pass Saturn. After 11 days, it would be farther than Neptune, the most distant planet in our solar system. Of course, we're not worrying about real-life problems like fuel or hitting space rocks. After flying for 15 months, the ship would have gone 1 light-year. But then, weird things would start to happen because of Einstein's special theory of relativity. At first, it seems like the ship could just keep speeding up forever. But there's one big rule. Nothing with mass can ever go as fast as light. Take protons, for example. In the Large Hadron Collider, the strongest particle smasher on Earth, protons can be pushed to nearly the speed of light, about 299,792,455 meters per second. You might think that just adding 3 more meters per second would push them past the speed of light, but no matter how much energy you use, they can only get closer, not actually reach it. If this rule didn't exist, our ship would hit the speed of light in 45 days. But that's not how the universe works. Instead, as the ship gets closer to that limit, strange things happen. According to relativity, the faster something moves through space, the slower time moves for it. To people watching from far away, the ship would seem to slow down as it gets near the speed of light. The people inside would appear to be moving slowly, but inside the ship, everything would feel normal. The crew wouldn't notice anything strange. In fact, it would seem to them like time outside the ship was going faster. At 15 months, when the ship hits 87% of the speed of light, time slows down a lot. But even near light speed, time doesn't slow down evenly. It slows more and more the closer you get to the speed of light. On the 15th of October in the year 1991, an amazing and puzzling particle from space hit Earth. Scientists were so surprised by it that they called it the "Oh my God" particle. And when you hear what made it special, you'll understand why. This tiny particle had an unbelievable amount of energy, as much as a baseball moving at about 94 kilometers per hour. Just think about that. One tiny particle, so small you'd never see it, had the same energy as a flying baseball. But what really shocked scientists was its speed. It wasn't just fast. It was moving at 99.999999999999999999999999999999999999999% of the speed of light. That means it was just a tiny bit away from going as fast as light itself, something that no known object with mass is supposed to be able to do. To this day, scientists have no idea what could have possibly given this particle such an extreme boost in speed. What kind of force or event in the universe was strong enough to speed it up so much? No one knows. However, recent findings using the Telescope Array project suggest that this particle may have come from an area about 20 degrees wide in the direction of the Ursa Major group of stars. That's all the information we have for now, but even that small bit of knowledge brings up more questions than answers. Just thinking about the possible cause of such an amazing event is enough to give you chills. One of the strangest parts of this event is what happens to time when something moves at almost the speed of light. The effects of time slowing down were so strong for this particle that, from its own point of view, time was almost standing still. In fact, compared to someone who isn't moving, time for this particle slowed down by a factor of 300 billion. To explain that better, let's think about a trip across space. If people wanted to travel from Earth to the Andromeda Galaxy, which is about 2.5 million years away at the fastest speed we know of, it would take them exactly that long, 2.5 million years. But for this particle, the same trip would have felt like it took less than 5 minutes. Now, if you think that's amazing, let's take this idea one step further. What if a spaceship could move at this speed? What would happen if it just kept going and never stopped? If a spaceship kept moving far away from Earth, there's a certain point in the universe, an invisible line about 8.3 billion light-years from us, that it could never come back from. Not because there's a wall, but because space itself is growing larger. At that distance, space is pulling away from Earth faster than light can travel. This means that no matter how fast the spaceship moves, or how much power it uses to come back, it would still be getting farther away instead of closer. This doesn't break any laws of physics because the spaceship isn't going faster than light. It's the space around it that is stretching that quickly. To help understand this, think of a slinky toy. If you pull on both ends, each coil only moves a small bit, but the coils on the far ends end up very far apart. That's what's happening with galaxies in space. They're not moving through space faster than light, but the space between them is growing at that rate. So if a spaceship goes past the 8.3 billion light-year line, it's over. No matter what the crew does, they would never be able to come back. It's a scary idea, being lost in space forever, with no way to return to where you came from. Now, let's take a step back and think about something even harder to believe. The part of the universe we can see with our telescopes, the visible universe, is about 46 billion light-years across in every direction. But because the universe keeps growing, that visible area is getting bigger. Scientists think it will grow to about 61 billion light-years. But here's the problem. Just because we can see something doesn't mean we can reach it. Because of dark energy, a strange force that is speeding up the universe's growth, the cosmos has been split into different parts. The galaxies closest to us, within 15 billion light-years, can still be reached. If we could travel at the speed of a light, we could, in theory, go there. But beyond that, things get even weirder. Galaxies that are between 15 and 46 billion light-years away can still be seen, but we can never get to them. No matter how fast we go, they're moving away faster than light. Even more surprising, there are galaxies that are already farther than 46 billion light-years from us. These galaxies are totally hidden from us today, but in the very far future, their light will finally reach Earth. This means that future humans, if they are still around, will be able to see galaxies we can't see now. But beyond the 61 billion light-year limit, there are galaxies that we will never, ever see. Not now, not in 1 trillion years, not even once. They are past the edge of what we can ever reach or detect. To show how fast the universe is growing, let's look at one of the farthest galaxies we've ever found, GNZ 11. This galaxy is 13.4 billion years old, which means the light we see from it today was sent out just 400 million years after the Big Bang. But because space has stretched so much since then, GNZ11 is now actually 32 billion light-years away from us. We can still see this galaxy now, but soon its light will fade away. In time, it will vanish forever. The light GNZ11 is sending out right now will never reach us. The universe is pushing it away too fast, and this isn't just happening to GNZ11. The truth is much more troubling. Scientists think that more than 96.7% of the galaxies we can see right now have already moved beyond our reach. 98.6% of all the galaxies we will ever be able to see are already gone into the fast-growing universe. In total, we should have been able to see 4,700 billion galaxies since we started watching the skies. Out of those, 4,634 billion galaxies have already vanished from our reach. That leaves just 66 billion galaxies we can still reach, and it gets even worse. Every second, around 60,000 stars leave our view forever. That's tens of millions of stars disappearing every day, stars that used to be in our visible universe but are now gone for good. Think about looking up at the night sky and seeing stars that no longer exist. They might have died millions or even billions of years ago, but their light is only now reaching us. Now, think about that on a much bigger scale. There are entire galaxies that right now are disappearing, not because they are blowing up, but because the universe is growing so fast that any new light they send will never get to us. So for all practical reasons, those faraway galaxies no longer exist to us. They are still out there somewhere, but we can never reach them again. We can't send them messages, we can't see what happens to them next, and they can't affect us in any way. In a way, they've been erased from our version of the universe, locked away forever. If the force making the universe grow keeps getting stronger, then even the closest galaxies will float away into emptiness. Over time, every galaxy will be alone. Stars will use up their fuel and go dark, leaving behind cold, dead remains. The tiny parts that make up everything, planets, people, even atoms, will break down. Even black holes, which seem like they last forever, will slowly fade away because of something called Hawking radiation. This takes a time so long it's hard to even understand, but in the end, even black holes will be gone. What will be left? Just empty space going on forever, filled only with dark energy. Dark energy is one of the strangest ideas in today's science. Unlike gravity, which pulls things together, dark energy does the opposite. It pushes space apart. What's even stranger is that as space grows and gets more empty, dark energy doesn't get weaker. It stays the same, or might even grow stronger. This creates a loop. The universe grows, which makes more empty space, which gives dark energy more room to work, making the universe grow even faster. This keeps happening, meaning the universe will keep growing faster and faster. In time, things happening in one part of the universe won't be able to affect other parts. Everything will be so far apart that even light won't be able to cross the distance. Now, let's think about an amazing idea. What if we built a spaceship that could move almost as fast as light? If the crew took a trip and their ship's clock reached 200 years, an almost impossible amount of time would have passed for the rest of the universe. That time, 10 to the power of 41 years, that's a 1 followed by 41 zeros. By then, the universe would look totally different. Space would be stretched out so much that the ship might be the only thing left in its part of the universe. No stars, no planets, no galaxies, just never-ending darkness. The crew would be flying through a universe that had already gone completely empty. Could they ever find the edge of the universe? The answer is no. The growth of space would beat even their near-light speed travel. No matter how fast they went, they would never reach an edge, because the universe doesn't have one. This brings us to a strange and hard-to-understand idea. What if the universe has no edge but still isn't endless? For thousands of years, people have wondered whether the universe goes on forever, or if it stops somewhere. A well-known question, asked more than 2,000 years ago by the Greek thinker Archytas, makes us think deeply. If you stood at the edge of the universe and threw a spear, what would happen? Would it hit a wall and bounce back? If it did, what's on the other side of that wall? And if it passed through, then the universe must go on. So no matter how far we go, there must always be more, meaning the universe must be endless. This question confused thinkers and scientists for centuries. But what if the answer isn't just endless, or not endless? What if the universe has no edges, but still has a limited size in another way? To understand this, we need to look at something found in the 19th century by one of the greatest math experts in history, Carl Friedrich Gauss. For most of history, people believed the corners of a triangle always add up to 180 degrees. That's true on flat surfaces, but Gauss thought space might not be completely flat. Think of living on a huge ball, like a planet's surface. If you draw a small triangle on the ground, its corners will still add up to 180 degrees. But if you draw a really big triangle covering a large part of the planet, something odd happens. The corners will add up to more than 180 degrees. That's because the surface is curved. Gauss wondered if the same thing might be true for space. If space was curved, then the shapes and rules we know might not work the same on a big scale. To test this, Gauss quietly measured the angles of a huge triangle formed by 3 mountaintops in what is now Germany. He wanted to see if their angles added up to more than 180 degrees, but the change was too small to be sure, so he never made it public. Years later, Albert Einstein's idea of general relativity showed that space really is curved by gravity. Later measurements showed that near Earth, triangle corners can add up to a little more than 180 degrees, around 180.2 degrees. So what does this say about the shape of the universe? If space is curved in a big way, it could mean the universe is limited in size but has no edges. Think of the surface of a balloon. A creature living on the surface would never find an edge, but their world would still have a set size. If they kept moving in one direction, they would end up back where they started. If our 3-dimensional universe works the same way, it might not have an edge, but it also might not go on forever in a straight line. Instead, it could fold back on itself in a way that's hard for us to see. So where does that leave us? The universe is growing faster and faster, pushed by the strange power of dark energy. The galaxies we see now will one day move out of our reach, and in the end, all that will remain is a vast, quiet emptiness. We often think of the universe as going on forever in all directions, but what if that's not exactly true? Scientists are working hard to figure out the real shape of the universe, not just how it looks to us from inside. A key clue to this mystery is something called curvature, a math idea that could help us find out if the universe is really endless or if it's somehow wrapped around itself. At first, this seems impossible to understand, but let's look at the shape of the Earth. If you start walking in one direction, you won't fall off an edge. You'll just keep going until you come back to where you started. Earth's surface looks endless up close, but it's actually curved into a closed shape. Now, think of the same idea, but in 3-dimensional space. Could the whole universe be curved so that if you moved in a straight line for a long time, you'd end up back where you began? It's a very hard thing to picture, even for the smartest scientists. Our minds can't really see it, so we use math to help us guess what might be true. Over the years, scientists have done a lot of research on this topic, and have found not just one but 18 different possible shapes, or topologies, for the universe. These possible forms fall into 2 main groups: orientable and non-orientable universes. To understand the difference between these 2 types, let's look at a strange 2-dimensional shape called the Mobius strip. You can make a Mobius strip by taking a long strip of paper, giving it one twist, and then joining the 2 ends together. What makes this shape so special? If you put a dot on the strip and start drawing a line along the surface without stopping, you will eventually return to where you started, but flipped. That means the direction is reversed. If you had written something on one side of the strip, when you come back to your starting point, the writing would look like a mirror image. In geometry, surfaces like this are called non-orientable, meaning they have paths that flip the direction of objects moving through them. On the other hand, shapes like a ball or a donut, called a torus, are orientable, which means they do not flip anything. Now, imagine that the entire universe is shaped like a Mobius strip, but in 3 dimensions. If this were true, something very strange would happen. If you travelled in a straight line far enough, you would end up back where you started, but everything would be reversed, like a mirror image. This may sound like something from a science fiction story, but in math, it is a real possibility. However, most scientists who study the universe do not believe we live in that kind of universe. One reason is that if the universe were non-orientable, there would likely be places where normal matter and antimatter, its opposite form, would meet. This would create energy that we could detect, but so far we haven't seen anything like that. That doesn't mean it's completely impossible. it could still be true in parts of the universe that are far beyond what we can see. One way scientists check these ideas is by measuring how space bends over huge distances. Near heavy things like stars and black holes, space is definitely bent. But when we look at space on a much larger scale, the data shows that the universe is incredibly flat, at least in the parts we can observe. If the universe is really flat, that has big consequences. It means the universe could go on forever, because a universe that goes on without end would look flat when seen on a very large scale. And this leads to some amazing ideas. A scientist named Max Tegmark looked into this in his book, Our Mathematical Universe. He figured out that the number of ways particles can arrange themselves in the part of the universe we can see is about 10 raised to the power of 10 raised to the power of 118. That's a number so huge, we can't truly imagine it. But if the universe really is endless, then something amazing must be true. Somewhere out there, way beyond what we can see, there must be another Earth exactly like ours. Imagine drawing a straight line from Earth in any direction. If you travelled a distance equal to 10 raised to the power of 10 raised to the power of 118 times the size of the observable universe, you would, in theory, reach a copy of Earth, with a copy of yourself, thinking the same thoughts right now. This idea might seem even stranger than a universe with mirrored space. But unlike the Mobius strip idea, where reality is flipped, an endless universe means that every possible arrangement of particles must happen somewhere, no matter how unlikely. Now, let's take this thought even further. What happens if space is not just endless, but time is endless too? The answer is simple but deep. In a universe that has no end in space or time, everything that can happen will happen, eventually. Even if we think of a huge empty part of space with no particles at all, modern science says that this space is never completely empty. Tiny energy fields, called quantum fields, are always shaking a little. These tiny shakes, called quantum fluctuations, are a basic part of how the universe works, thanks to Heisenberg's uncertainty principle. If you wait long enough, these tiny shakes could cause very strange things to happen, like whole structures forming by chance, or even a whole new universe popping into existence from nothing. As wild as that sounds, it's actually something that modern physics predicts. Imagine a universe so huge and endless that even the most impossible things will happen, not just once, but many times, if you wait long enough. You might think, are you seriously saying that if we wait long enough, something like a grand piano could appear out of nowhere in the middle of empty space? As strange as it sounds, some of the top scientists in the world, Anthony Aguirre, Sean M. Carroll and Matthew C. Johnson, have studied this idea seriously. They even did the math, and found that if you waited for a time so long it would make the current age of the universe seem like the blink of an eye, something like a trillion times longer, you would eventually see that piano show up out of thin air. As hard as this is to believe, it follows from what we currently know about the laws of physics. The less likely something is, the longer you have to wait. But in a universe that lasts forever or goes on forever, or both, even the most unlikely things will happen. Not just once, but an infinite number of times. That's the strange truth about infinity. If time truly never ends, then our universe will repeat itself endlessly. You will watch this exact video again, not just once, but over and over forever. Some people find this exciting, others might find it disturbing. It makes us wonder, is the universe really infinite, or does it have some kind of edge? Some scientists think the universe could still be finite, just extremely large and shaped in ways we haven't figured out yet. The tools we use today tell us the universe seems flat, with an accuracy of 99.75%. But if it's not perfectly flat, then it must be at least 400 times bigger than the part we can see, stretching across a mind-blowing 37,200,000,000,000 light years. But here's the twist. Even if the universe is closed, that doesn't mean it curves the way we might expect. Think about a cylinder. It looks flat from the side, straight lines stay straight, but it can still go on forever in a loop. The universe might work the same way. Some scientists even think the universe could be shaped like a four-dimensional torus, a shape where space seems flat. But if you go far enough in a straight line, you end up back where you started. A four-dimensional sphere would behave differently. Angles in a triangle would add up to more than 180 degrees, and straight lines would eventually meet. As three-dimensional beings, we may never fully understand what the universe really looks like. To see it clearly, we would need to live in 4 dimensions. And here's a surprising idea. The edge of the universe is not far away. It's all around us. Imagine a place where nothing exists for an unimaginable distance. A place so completely empty that it feels as though time itself has come to a complete stop. There is no light, no stars, no galaxies, just an endless hole of total darkness stretching for what seems like forever. We live on a planet that goes around the Sun, which in turn is part of the Milky Way galaxy. The Milky Way does not exist by itself. It is part of a group of about 50 galaxies that make up the local group. This local group itself is just a small part of a much bigger bunch called the Virgo supercluster. But it doesn't stop there. The Virgo supercluster, along with many other superclusters, is a piece of something even bigger, a huge structure called the Laniakea supercluster. Unlike planets or moons that go around a center, these giant galaxy groups do not circle around one spot. Instead, they move under the pull of gravity from a strange and powerful mystery called the Great Attractor, which stays hidden at the center of our local space neighborhood. Yet, our focus today is not on this strong force. Instead, we will look into something much more spooky: the huge, lonely nothingness that lies in front of it. This empty area is called the dipole repeller, a place where gravity's pull is so weak that matter seems to stay away from it. These empty spots in space are called voids, and they are some of the biggest structures in the universe, making up most of its space. If we could see the universe from far away, it would look like a giant web, galaxies joined by glowing strings, separated by huge pitch-black holes. And among these voids, there is one that stands out as one of the most confusing and scary of all: the Bhuta's Void. When we look up at the night sky, it seems like the stars are spread out evenly across the sky. But this is a trick. Stars are actually bunched together in galaxies, and those galaxies form groups held by gravity. The spaces between these groups may seem big, but they are small when compared to the size of cosmic voids. The Bhuta's Void is one of the biggest known voids in the whole universe. It is found about 700 million light-years away from Earth, in the direction of the Bhuta's group of stars, which is how it got its name. This huge area was first found in the year 1981 by space scientist Robert Kirshner and his team. From the moment it was found, scientists have been confused by its giant size and strange emptiness. To understand just how big the Bhuta's Void is, think about this. Its width is guessed to be about 330 million light-years. To make that easier to understand, this one void covers 27% of the total width of the part of the universe we can see. To compare, the Milky Way galaxy, which is already incredibly big, is only about 100,000 light-years wide. That means you could fit over 3,000 Milky Ways next to each other inside this void. When scientists first started studying the Bhuta's Void, they thought they would find thousands of galaxies spread throughout the area. But what they found shocked them. At first, they could only see 8 galaxies inside this huge space. That number has gone up since then, but even now only 60 galaxies have been found. To see how strange this is, think about the Andromeda Galaxy, our closest galaxy neighbour. It is about 2.5 million light-years away from us. If galaxies were spread evenly across the universe, the Bhuta's Void should have at least 2,000 galaxies, but instead, it has only a small part of that number. Space scientist Greg Aldering from the University of Minnesota explained how big this mystery is in a clear way. If our Milky Way galaxy was sitting at the center of the Bhuta's Void, we would not have known that other galaxies even existed until the 1960s. The huge emptiness would have kept us from seeing them with telescopes before that time. The deep emptiness of the Bhuta's Void has led many scientists to call it one of the strangest places in the universe. The number of galaxies in this area is so low that it almost doesn't make sense. To see why this is so weird, let's compare it to our own space neighborhood. Within just 3 million light-years, our Milky Way galaxy has over 24 nearby galaxies. In contrast, the Bhuta's Void has an average space between galaxies of over 10 million light-years, 4 times the distance between the Milky Way and Andromeda. If the universe were evenly spread out, this void should have at least 10,000 galaxies. Scientists have tried to figure out the true size of the Bhuta's Void. Since regular units are not good enough to show such huge distances, They use a unit called the parsec, which is the same as 3 light years. Using this unit, they guessed that the full size of the Bootes void is about 236,000 cubic megaparsecs. To put it simply, this void is so big that if it were filled with galaxies at the normal amount, it could have thousands of times more matter than it does now. So what is inside the Bootes void? The strange answer is almost nothing. It is a space desert, almost fully empty of matter. Unlike the busy areas of other galaxies, where stars, planets, gas clouds, and space dust move together in a wild dance of birth and death, the Bootes void is strangely quiet. Even tiny bits, like photons, the tiny pieces of light, are rare in this dark space. This is why some scientists call the Bootes void the final space desert. The Bootes void is so dark and lonely that some researchers have said it feels like time itself seems to stop there. In most galaxies, the actions between stars, planets, and space forces move time forward, causing change and motion. But in the Bootes void, nothing seems to happen. There is no big action, no strong forces working, just deep stillness stretching across millions of light years. To make it clearer, dust and dirt, common things on Earth, are almost completely missing here. But even more amazing is that particles themselves, the very tiny pieces that make up everything, hardly ever touch each other. If they do, it could take thousands upon thousands of years for that to happen. This deep emptiness causes something strange. When streams of neutrinos, which are almost weightless, go into one side of the void, they come out the other side fully unchanged. The same thing happens to photons, the light pieces. Matter, which is much heavier, doesn't have this luck. It gets slowly pulled toward the outer parts of the void, where a few lonely galaxies still remain. Because of this special feature, where light and energy stay the same, the Bootes void might one day become the perfect time storage. Imagine sending a beam of photons across this huge gap, only for it to be found hundreds of millions of years later, when it reaches the other side, unchanged, a sign from a time long gone. But more than being a space archive, this place could also serve a more future use. With no space dust to slow them down, smart spaceships could use this emptiness as the best testing area, maybe one day reaching speeds as fast as 99.99% of the speed of light. Yet, the biggest mystery about the Bootes void is not just what it could be used for, it's how it ever came to be at all. When compared to the rest of the universe, it is a mystery unlike anything we've ever seen. Some scientists think it was made when a bunch of smaller voids came together, much like how small soap bubbles join into one big bubble. To support this idea, space scientist Greg Aldring noticed that the galaxies inside the void seemed to be lined up in strange tube-shaped patterns. He thought that these galaxies might be leftovers from the borders where the smaller voids once touched before becoming one huge emptiness. If the universe lasts long enough, even these galaxies might one day be pulled out by the never-ending pull of gravity, leaving behind an even deeper, darker nothingness. Some people have guessed that the Bootes void was not made in a natural way at all, that it might be the result of a very old, super-advanced civilization. According to this idea, a Kardashev Type 3 civilization, one able to use the energy of whole galaxies, might have slowly moved across this area. As it grew, it could have made each star dim or even disappear by covering it with giant Dyson spheres, machines made to trap all the star's energy. This could explain why the void is nearly a perfect sphere and why it has almost no visible matter. Since the void is about 700 million light-years from Earth, and since smart life in the universe could have started as early as 4 billion years ago, such a civilization would have had more than enough time to pull off this amazing piece of space engineering. Have you ever wondered if there might be another version of yourself living a completely different life, in a world that exists next to ours? Could it be possible that what we think of as our reality is just one of many? Some scientists and deep thinkers believe that our view of life as a smooth journey through time and space might be nothing more than a trick of the mind. Instead of moving along just one path, our lives could be a constantly splitting chain of events, branching off at every moment into endless possibilities. Let's look into amazing discoveries that might suggest the multiverse is real. We'll talk about a strange kind of energy that fills the whole universe, called the Cosmic Microwave Background Radiation, CMB, and why it has excited scientists for so long. We'll look at clues that might show other universes are real. Think about whether there could be another life beyond this one, and explain how the famous thought puzzle called Schrödinger's cat and the work of Albert Einstein are linked to it all. In the year 1948, when a brilliant scientist named George Gamow, who was born in Russia but later moved to the United States, made a bold guess. He believed that if the universe began with an unimaginably strong explosion known as the Big Bang, then leftover energy from that event should still be around. Based on his math, this energy should have a temperature of about 50 degrees Kelvin, which equals a freezing negative 2,167 degrees Celsius. But Gamow's guess was off by more than 10 times. When this energy was finally found, its real temperature was only 2.7 degrees Kelvin, just above absolute zero. The discovery happened completely by chance. In the year 1965, two American scientists named Arno Penzias and Robert Wilson were working at Bell Laboratories. They were using a radio antenna that had been built in the early 1960s for one of the first satellites used for communication. The satellites were no longer working, and they had been safely burned up when they re-entered Earth's atmosphere. Penzias and Wilson were trying to study the light waves given off by neutral hydrogen, a very common element in the universe. But their work kept getting interrupted by a strange background noise. No matter what they did, the weird microwave sound stayed. At first, they thought the noise might be from military testing or radio signals from New York City. When that didn't explain it, they even guessed that pigeon droppings inside the antenna might be causing the odd signal. But after cleaning the antenna carefully, the noise was still there. Only later did they realize they had found something incredible, the exact energy that scientists had been hoping to find, the cosmic microwave background radiation. For their accidental but historic discovery, Penzias and Wilson were given the Nobel Prize in the year 1978. What made this discovery so important was that it backed up a major part of the Big Bang theory. Scientists soon saw that this energy wasn't just coming from one direction, it was everywhere. No matter where you looked in space, the energy had the same temperature. It was like an unseen ocean surrounding everything. Even though the CMB seemed to be very smooth, there were tiny changes in its temperature, just as the theories had predicted. On average, these changes were about 18 microkelvin, which is a very tiny difference. If you could draw a map of this energy's temperature across the sky, it would look like a patchwork quilt or soft ripples on a pond. Jump ahead to the year 2004, when a NASA satellite called WMAP was studying the cosmic microwave background radiation in great detail. This probe was made to map the small changes in temperature that had been around since the universe was just 380,000 years old. But when scientists looked closely at the data, they found something truly strange. A cold area in the radiation that was much bigger and colder than anyone expected. So why is this cold spot so strange? Its temperature is much lower than the nearby areas. While the usual temperature change in the CMB is about 18 microkelvin, this region was about 70 microkelvin, and at its centre it might drop to around 50 microkelvin. Imagine an ocean where the average wave is only a few centimetres high, and then out of nowhere you see a huge wave that's several metres tall. That's how odd this cold spot is compared to the rest of the universe. Its size is hard to believe. The cold spot is thought to be nearly 2 billion light-years wide. For comparison, our Milky Way galaxy is only 100,000 light-years across. This means the cold spot could hold almost 20,000 galaxies the size of the Milky Way inside it. If that doesn't show how big it is, think of this. The land area of the United States is about the same as 8,000 New York cities. Now picture a space so huge it makes all that look tiny, by a truly unthinkable amount. Scientists believe this cold spot matches an enormous empty region in space, where there are far fewer galaxies, stars, and other things. This place, found in the constellation called Eridanus, has been named the Eridanus supervoid. If you somehow travel to the centre of this emptiness, you would be surrounded by total darkness. No stars, no galaxies, just a cold, endless stretch of nothing. It would be a place like nothing we have ever known, without light, gravity, or any sense of direction. It might be one of the darkest and strangest places in the entire universe. Some scientists have guessed that this supervoid might not just be an empty part of space. One interesting idea says the Eridanus supervoid could be what's left behind after our universe bumped into another universe in the multiverse. In other words, the cold spot might be a cosmic scar, a leftover mark from when two different universes touched. If this idea is correct, then the cold spot could be one of the first real clues that other universes exist. While this idea is still just a guess, it is being seriously studied by some of the best minds in science. For many years, scientists have looked at the large empty areas in space called voids. These are huge regions where galaxies and galaxy clusters are rare, making them some of the emptiest places in the known universe. Compared to more crowded parts of space, these voids have about 10 times less matter. The first time these voids were found was in 1978, when two astronomers named Stephen Gregory and Laird Thompson, working at Kitt Peak National Observatory in Arizona, noticed these strange gaps in the cosmic web. These voids can be very different in size, from 30 million to 300 million light-years wide. But one void, the Eridanus supervoid, stands out. It is shockingly big, nearly 2 billion light-years across, making it much larger than any other void ever found. This finding brings up troubling questions. If the universe spread out evenly after the Big Bang, as most scientists think, how could something this huge and this empty exist? The usual Big Bang story can explain regular voids, but something as large and as cold as the Eridanus supervoid doesn't fit. It's a true oddity, one that has left scientists scratching their heads. Since it was found, many different ideas have been suggested to explain this strange part of the universe. These range from scientific to truly mind-blowing. Let's take a closer look at them. One of the early ideas was that the Eridanus supervoid might actually be a supermassive black hole, a giant gravity monster that eats up everything near it, leaving behind a huge empty space. Some people even wondered if this cosmic giant might keep growing, swallowing up planets, stars, and even our galaxy. But don't worry, Earth is safe. First, the void is 3 billion light-years away, so anything dangerous happening there would take an extremely long time to reach us. Second, the size a black hole would need to be to create such a void is so huge that it goes beyond what science can explain right now. To put it simply, even a black hole with a weight of 100 million suns would be much smaller than our sun when it comes to its actual size. That means, even with its huge pull of gravity, it could not make such a huge empty space just by eating up matter. Another idea involves dark matter, the strange invisible stuff that makes up most of the weight in the universe. Unlike normal matter, dark matter doesn't interact with light or other kinds of energy, so we can't see it, but we can notice it by the way its gravity affects other things. Based on widely accepted ideas about the universe, every part of space, including the empty areas, should still have at least a little dark matter. But when scientists studied the Eridanus supervoid, they saw something odd. There was no sign of dark matter at all. If this huge empty space had a normal amount of dark matter, its radiation would look different, and its pull of gravity would be stronger. This missing dark matter leads to a worrying idea. What if dark matter doesn't exist at all? If the Eridanus supervoid really has no dark matter, it could mean that the whole Big Bang idea, the very base of how we think the universe began, is not finished, or even wrong. Without dark matter, many of the math formulas used to explain the universe just wouldn't work. But before we throw away many years of science, it's important to remember that there is still a lot of proof that dark matter is real. The question remains, why does this one area seem to be missing it? If black holes and missing dark matter can't explain the Eridanus supervoid, then what can? Some scientists think the answer might come from outside our universe itself. According to an amazing idea, this empty space might be the first real proof of the multiverse. The idea that our universe is just one of many that all exist side by side in a huge cosmic sea. But how could we ever see signs of another universe? The answer might be found in what's called the cosmic microwave background, CMB radiation. This is the faint old light left over from the Big Bang, and it acts like a fingerprint of the early universe. Oddly, when scientists looked at the map of the CMB, they found a cold spot exactly where the Eridanus supervoid is. This means that something very strange happened in that spot billions of years ago, something that normal science can't fully explain. Some scientists think that long ago our universe might have hit another one, leaving behind a mark on the cosmic microwave background. In other words, the Eridanus supervoid might be the place where two bubble-like universes touched. This idea is backed by the work of scientists Anthony Aguirre, Matt Johnson, and Matt Kleben. who showed that if our universe ever crashed into another, it would leave behind a clear, round mark in the CMB. That is exactly what scientists see in the Eridana supervoid. If this idea is true, it would be one of the biggest discoveries in all of history. It would prove that our universe is not alone, and that there could be many other universes, maybe even with their own stars, planets, and life. To understand why the multiverse idea is taken seriously, we need to take a short trip into quantum physics, the part of science that deals with the tiniest pieces of matter. One of the most well-known experiments in quantum physics is the double-slit experiment. In this experiment, when scientists shine light or fire tiny bits of matter through two narrow openings, they see a pattern of waves on the screen behind them, like the particles are acting like waves. But when they try to watch them closely, the particles act like solid objects instead. This strange behavior shows that particles can exist in more than one state at the same time, a rule called superposition. Some scientists think this supports the many worlds idea, which says that each time something happens in quantum physics, the universe splits into different versions. If this idea is right, then the multiverse is real, and the Eridana supervoid could be the first real sign that another universe once crashed into ours. Imagine you're standing at the edge of a quiet lake, holding a small rock in your hand. You throw the rock into the water and watch ripples move out in perfect circles. Now, imagine throwing two rocks at the same time, just a little apart. What happens? The ripples from both rocks crash into each other and make a pattern, a mix of high and low waves where they either add up or cancel each other out. This is called an interference pattern, and it's something that naturally happens with waves. But what if someone told you that tiny pieces of matter, the basic parts of everything around us, can act like those waves? And even stranger, what if just watching them could change how they act? This is one of the biggest mysteries in science, and it all starts with a simple test. Scientists wanted to see how waves and particles behave when they go through a small gap, or slit. They set up a wall with a thin slit in it, and behind it, they placed a screen to show where the waves or particles would land. When they sent waves, like water waves or light, through the slit, the waves spread out and made a bright line on the screen. No big surprise there. Then they tried the same thing with tiny particles like electrons, which are part of atoms. When they sent the electrons through the slit one by one, they hit the screen in a straight line like little bullets being fired. Everything seemed normal. Next, the scientists added a second slit and did the test again. This is when things got weird. When waves went through both slits, they didn't just make two bright lines. Instead, they made a pattern of many light and dark lines. This showed where the waves joined together or cancelled each other out. But what about particles? If electrons were like tiny bullets, you'd expect them to go through one slit or the other and make two lines, right? That's not what happened. Instead, the electrons made the same wave-like pattern as before. Instead of two lines, they made many bright and dark lines. But how could single particles, shot one at a time, act like waves? At first, scientists thought maybe the electrons were hitting each other and causing the pattern. So they slowed it down and fired one electron at a time. Each one travelled alone, with no others around to bump into. But even when sent one by one, the electrons still made the wave pattern. That meant each electron was somehow acting like a wave, going through both slits at the same time and interfering with itself. To figure this out, the scientists tried watching the electrons. They put a detector near the slits to see which one the electrons went through, and then something even weirder happened. As soon as they watched the electrons, the wave pattern disappeared. The electrons started acting like regular particles again, making just two lines, like tiny bullets. This showed that just watching the electrons changed how they acted. But how? Was the electron somehow aware that it was being watched? Did the universe act differently just because someone was looking? This strange result led to some of the most surprising ideas in science, ideas that could change how we understand everything. One of the most famous explanations came from scientists Werner Heisenberg and Niels Bohr in the early 20th century. Their idea, called the Copenhagen interpretation, says that before we look at a particle, it doesn't have a single clear state. Instead, it exists in all possible states at once, like a blurry mix. When we look at it, we force it to choose one of those states. In other words, an electron isn't in one place or another until we check. This idea upset many scientists, including Albert Einstein, who said, God does not play dice. He didn't believe the universe worked based on luck or chance. Another scientist, Erwin Schrödinger, came up with a thought experiment to show how strange this idea was. Imagine you put a cat in a box. Inside the box there is an atom that has a 50-50 chance of breaking down in 1 hour. If it breaks down, it sets off a trap that releases poison and kills the cat. If it doesn't break down, the cat stays alive. But based on quantum rules, until you open the box and check, the atom is both broken down and not broken down at the same time. And since the cat's life depends on the atom, the cat is also both alive and dead at the same time. Only when you open the box does reality decide if the cat is alive or not. This sounds crazy, and Schrödinger meant it to show how strange the idea really was. He was saying, this can't possibly be how the world really works. Another possible explanation, known as the many worlds idea, says that all possible outcomes actually happen, but in separate worlds. In this idea, every time you make a choice, the universe splits into many parallel worlds. If you toss a coin, there is one world where it lands on heads and another where it lands on tails. Using this idea to explain the double slit experiment, when an electron goes through the slits, it goes through one slit in one world and the other slit in a different world. We only see one result because we are inside just one of these countless branching worlds. This idea sounds like something from science fiction, but some of the world's best scientists take it seriously. Now, let's take it a step further. If looking at something can change what happens, what if the world around us is not even real? Some scientists think that our whole universe might be a simulation, like a huge computer game. In a video game, things only fully appear when the player looks at them. What if electrons act the way they do because we are inside a fake world, and things only show up when someone looks at them? It sounds strange, but there are strong reasons behind this idea. If it is true, it would mean our universe is not the real one, but just one of many made-up worlds. At the farthest edges of the part of the universe we can see, there are some truly amazing and puzzling things happening. Things that help us understand just how big, strange, and beautiful space really is. The observable universe is like a giant bubble surrounding us. This bubble stretches out as far as light has been able to travel since the universe began, about 13,800,000,000 years ago. But this outer limit is not a wall or an edge in the way we usually think of it. Instead, it's more like a horizon, a boundary that shows us how far we can look based on the age of the universe and the speed of light. And near this edge, space is full of strange and powerful events that help us learn more about how everything began. One of the most important things found near this boundary is something called the cosmic microwave background radiation. This is a faint glow of light that fills the entire universe. It's like the leftover heat from when the universe was just born, from the time just after the Big Bang. You can think of it like the soft afterglow from a fire that has just gone out. Even though this light is very weak now, it carries important information. It shows us what the universe looked like when it was only about 380,000 years old, a time when it was still hot, thick, and full of tiny particles swirling around. By studying this ancient glow, scientists can figure out what the universe was made of, how it expanded, and what its early moments were really like. As we look farther out into space, we also see galaxies that are moving away from us at amazing speeds. This happens because space itself is stretching in all directions. The farther away a galaxy is, the faster it seems to be moving away. Some galaxies are so far out that their light will never reach us, no matter how long we wait. That means there are huge parts of the universe we will never see. Regions full of stars, planets, and energy that will forever stay hidden from us. Another strange effect seen near the edges of the observable universe is redshift. As galaxies move away, the light they send out gets stretched into longer wavelengths, which makes it look redder than it really is, just like the sound of a car engine changes as it drives past you. This change in light tells us how fast the universe is growing. The more redshift we see, the faster the object is moving away, and the farther back in time we are looking. And at these great distances, we can also spot giant structures that are still forming or are barely visible. These include faraway galaxies, huge webs of matter called cosmic filaments, and large clusters of galaxies held together by gravity. These structures show us the forces at work in the universe, slowly shaping everything over billions of years. The edge of what we can see is not empty or quiet. It's full of mysteries and clues. It helps us understand how the universe came to be, what it is made of, and even where we might be heading in the future. But there's more to this story. Some of the strangest and most powerful things in space are black holes and quasars. These objects remind us that the universe is full of surprises, many of which we still do not fully understand. A black hole is an area in space where gravity is so strong that nothing, not even light, can get out. It's like a bottomless pit in space. Because no light escapes, we can't actually see the black hole itself, but we know it's there because we can see what happens around it. When gas, dust, or even stars fall toward a black hole, they spiral in like water going down a drain. As this material spins, it heats up and shines brightly, sometimes brighter than whole galaxies, before it disappears into the black hole forever. This glow gives us clues that a black hole is hiding nearby, even though we can't see the hole itself. Quasars, on the other hand, are some of the brightest things in the whole universe. A quasar is powered by a supermassive black hole sitting at the heart of a galaxy. As material falls into the black hole, it releases a huge amount of light and energy. Quasars shine from incredibly far away, billions of light years out, so we are seeing them as they were long ago, when the universe was still very young. They help us study how galaxies formed and grew at the very edges of what we can see. But black holes and quasars also suggest there may be even more waiting to be discovered. They hint at the existence of distant areas filled with strange matter and forces we haven't yet seen or understood. They remind us that most of the universe is still a mystery, and that the more we learn, the more there is to explore. Another amazing part of the universe's structure is something called galactic superclusters. These are like the giant cities of space. Just as cities are made up of many neighborhoods, superclusters are made up of many galaxy clusters, each one filled with galaxies, stars, planets, and other cosmic objects. These superclusters are the largest known structures in the universe. If we think of the universe as a massive web, then the superclusters are the knots where many threads meet. They are held together by gravity and connected by strands of dark matter, which is a kind of invisible material that we can't see, but know is there because of how it affects other objects. Superclusters also shape how galaxies move. Their gravity pulls galaxies along like roads guiding cars. In this way, superclusters help organize the universe. By studying how these giant structures formed and how galaxies are spread out within them, scientists can understand how the universe grew over time. Superclusters even give us clues about dark energy, a mysterious force that is pushing the universe to expand faster and faster. So, galactic superclusters are not just random piles of galaxies. They are essential parts of the universe's blueprint, helping shape everything we see, and helping us uncover the story of how the cosmos came to be. And then, there are cosmic voids and filaments, two opposite but equally important features that help shape the universe on a huge scale. Again, picture the universe as a vast web. The filaments are like glowing threads, made of galaxies and dark matter, stretching across space and connecting everything. These filaments act like highways for galaxies, guiding how they move and how they gather together. In between the filaments are the voids, huge empty areas where there are very few galaxies. Even though voids may seem boring, they actually teach us a lot. These empty regions are growing faster than the crowded ones, and they help scientists understand how the universe is expanding and changing. Also, light from faraway galaxies bends as it passes through different areas of space, including these filaments and voids. This bending of light helps astronomers measure distances and map out the layout of the cosmos more accurately. Together, filaments and voids show us the true shape of the universe. They reveal how matter is spread out and how everything is linked by invisible forces acting across unimaginable distances. But the most mysterious parts of the universe might still lie far beyond what we can see. One of the biggest mysteries is something called dark matter. It makes up most of the mass in the universe, but we cannot see it because it doesn't shine or give off energy. Scientists only know it's there because of the way it affects how galaxies move. Without this hidden matter, galaxies would spin apart. So dark matter is like an invisible framework holding everything together. Then there is dark energy, another invisible force, but one that works in the opposite way. While gravity pulls things together, dark energy pushes things apart. It is the reason why galaxies are moving away from each other faster and faster. No one really knows what dark energy is, but its effects can be seen all across the universe. Some scientists even believe there could be extra dimensions, more than the 3 dimensions of space and 1 of time that we're used to. These other dimensions might contain new types of particles, strange forces, or even other universes with different laws of physics. And at the smallest scales, even empty space is not really empty. Thanks to quantum physics, we know that tiny bursts of energy, called quantum fluctuations, are always popping in and out of existence. These little bursts might be the key to understanding the deeper layers of reality. All of these wonders, from glowing aftershocks of the Big Bang to the invisible powers of dark matter and energy, show us that the universe is far bigger, deeper, and more mysterious than we ever imagined. Every discovery we make only leads to more questions, and that endless journey of curiosity is what makes exploring the cosmos such a thrilling adventure. The solar system is full of comets and asteroids, ranging from tiny rocks to giant space boulders, all moving at different speeds. Every single night new ones are found, sometimes dozens, sometimes even hundreds. For astronomers, spotting these objects has become a regular job, almost like clockwork. It rarely surprises them anymore. But something very different happened on the night of October 19th, 2017. That night shook the astronomy world to its core. Scientists across the globe lost sleep and couldn't think about anything else for weeks. Something very strange had appeared in the sky, and it was so unusual that they dropped everything they were doing to focus only on this one object. Even 2 powerful space telescopes, Spitzer and the legendary Hubble, were urgently turned to point at it. This strange visitor from space would later be named Oumuamua, which in Hawaiian means messenger from far away, or scout. We are now going to explore one of the most mysterious space objects ever seen, one that might help us solve a huge question known as Fermi's paradox. If life is common in the universe, why haven't we found any signs of it yet? But first, it's important to understand that, in the beginning, nothing about Oumuamua seemed that special. In fact, it wasn't even discovered by a person. These days, most space watching is done by robotic telescopes. There are many of them on Earth, and they're constantly scanning the sky for things that move quickly, usually not far away stars but nearby objects like asteroids or comets. This search goes on every single night, and thanks to these robots, astronomers have found more than 1 million asteroids in our solar system. On an average night, they find between 100 and 150 new ones. This has been going on for many decades now. So, when the robotic telescope Pan-STARRS, located in Hawaii and equipped with a 2-meter wide lens, spotted something new, no one thought much of it at first. It looked like just another comet. Its path through space was long and stretched out, much like how a comet moves. But then something strange came to light. As astronomers took a closer look, they saw that this object's path wasn't just stretched, it was hyperbolic. This meant that the object wasn't trapped by the sun's gravity like all the other comets and asteroids we've ever seen. It was not looping around the sun or orbiting it. Instead, it was flying through our solar system at an incredibly high speed. It wasn't from here at all. This was a stunning discovery. For the first time in human history, we had found something that came into our solar system from somewhere else in the galaxy. Until that moment, every single comet, asteroid, and piece of space debris we had ever studied was part of our own cosmic neighbourhood. They had been here for billions of years, circling the sun like children around a campfire. But Oumuamua had arrived from beyond. Now, it shouldn't be that surprising, really. Other stars have their own planets, comets, and asteroid belts, just like we do. It makes sense that sometimes these stars might fling out objects that drift through space. Still, we had never actually seen such a visitor before. At first, nobody knew what Oumuamua really was, but as scientists kept watching it, they noticed more and more strange things. The object was spinning, but its brightness kept changing in a strange pattern. That told astronomers that it didn't have a normal shape. In fact, it wasn't shaped like a ball or a rock. It looked more like a giant cigar, about 35 meters wide and nearly 200 meters long. This was like nothing we had ever seen before. Some people even wondered if it might be an alien spaceship. And even though that might sound like science fiction, the mystery only deepened. Astronomers traced the object's path through space, and realised it seemed to come from the direction of the constellation Lyra, and possibly the star Vega, a star known to have planets of its own. But there was a problem. If Oumuamua had been travelling for millions of years, then Vega would not have been in the same place when Oumuamua passed by it. Stars move too. So the mystery of its origin remained. Even stranger, Oumuamua had already passed very close to the Sun by the time it was discovered, closer than Mercury's orbit. Telescopes usually can't see objects coming from the Sun's direction, because the Sun's light blinds them. That's one of the biggest challenges in spotting dangerous space rocks. For example, we didn't see the Chelyabinsk meteorite until it exploded in Earth's sky on February 15, 2013, causing damage and injuries in Russia. In the same way, we only discovered Oumuamua after it had flown past the Sun and was already on its way out of the solar system. It had come screaming toward the Sun at about 90 kilometers per second, faster than anything else we've ever seen from our neighborhood in space. Then it passed by Earth, and we didn't even notice it until it was already beyond our planet's orbit. If it had been on a collision course, we would have had no warning at all. Thankfully, it missed us. When its strange shape was finally revealed, even scientists who usually doubted the idea of alien life were amazed. Some experts began to ask, what if this really is a probe sent by another civilization? Radio signals were sent toward it in hopes of getting a reply, but nothing came back. So most scientists went back to thinking it was just a natural object, though one like we had never seen before. As Oumuamua moved farther away from the Sun, something even more puzzling happened. It sped up. It used the Sun's gravity to change direction and increase speed, but without showing any of the normal signs of a comet, like gas or dust shooting out. That's how comets usually move faster. But Oumuamua stayed completely quiet. That left many wondering if it might actually be artificial. Even the direction it came from added to the puzzle. It seemed to arrive from the solar apex, the part of the sky that our solar system is heading toward as it moves through the galaxy. That raised an interesting thought. Maybe it wasn't that Oumuamua came toward us. Maybe we ran into it. Like a moving car hitting a pebble on the road, our solar system may have collided with a traveller that was already passing by. And then there's its bizarre shape. Out of the more than 1 million space rocks we've seen, none of them look like this, long and thin like a cigar. Some researchers think maybe it had been stretched by the gravity of a nearby star, while others suggest it might not be cigar-shaped at all. Some say it could have been flat like a pancake, which is even harder to explain. There are people who believe that to solve Fermi's paradox, we don't necessarily need to meet aliens face to face. Maybe all we need is to find something in space that defies every natural explanation we know. Something that makes us stop and say, this shouldn't exist. Maybe Oumuamua is that something. Even if we never find out what it really was or where it truly came from, its short visit was enough to remind us that the universe is full of surprises, and maybe, just maybe, we're not alone after all. One of the most jaw-dropping surprises in the history of modern space science discovered at the edge of the universe came from a tiny, faraway smudge of light in the sky, an ancient galaxy called GNZ 11. This wasn't just any galaxy. It was found at an unbelievable distance of 13.4 billion light-years from Earth. That means the light from it has taken 13 billion and 400 million years to reach us. So when we look at GNZ 11, we're not seeing it as it is now. We're seeing it as it was when the universe was still a newborn, only 400 million years old. That's just a blink after the Big Bang, which scientists believe happened about 13 billion and 800 million years ago. Back then, the universe was still lighting up for the very first time. Stars were just starting to shine, and galaxies were barely forming. It was the dawn of everything. So, spotting GNZ 11 was like discovering a fossil from the very beginning of time. But what really blew scientists away wasn't just how old it was how big it already had become. You'd expect a galaxy that young to be small, still forming, maybe with just a few stars scattered here and there. But GNZ 11 didn't look like that at all. It was already massive, filled with hundreds of billions of stars. That's the same kind of star count you'd find in our own Milky Way, a galaxy that has had over 13 billion years to grow, evolve, and develop into the beautiful spiral we see today. Finding a galaxy like GNZ 11, so early in the universe was like walking into a nursery and seeing a fully grown adult standing among the babies. It didn't make sense, and that wasn't all. GNZ11 wasn't just big, it was growing like crazy. It was forming stars at an unbelievable speed, far faster than what scientists thought was even possible back then. The only way this could happen was if the galaxy had access to a huge amount of gas the stuff stars are made of. Somehow, in the early baby years of the universe, this galaxy had found a way to gobble up massive clouds of gas and turn them into stars at a breakneck pace. This one discovery shook the entire foundation of what scientists thought they knew about how galaxies come into being. For a long time, experts believed that galaxies started out small and slowly got bigger over billions of years. But GNZ11 seemed to break all those rules. It looked as if it had leaped through time, growing into a fully formed giant galaxy before the universe had barely gotten started. Even more surprising, GNZ11 was not alone. As scientists looked deeper into space with powerful telescopes, they began to find more ancient galaxies just like it. These galaxies, also located billions of light years away, showed the same strange traits. They were huge, packed with stars, and even had shapes, like spiral arms or central bulges, that showed they were already organized and developed. Some even had something truly shocking at their centers: supermassive black holes. These black holes weren't the kind that form when a single star dies. No, they were monsters, each one containing the mass of millions or even billions of suns. And somehow, they had grown to this enormous size in just a few 100 million years, something scientists had always believed would take billions of years to happen. The big question became, how? How did these ancient galaxies grow so big, so fast? How did they become organized so quickly? And how did their black holes become so massive in such a short time? One idea that scientists are now seriously considering is something called direct collapse. Normally, a galaxy forms when gas clouds slowly pull together, making stars bit by bit over millions of years. But with direct collapse, a giant cloud of gas might skip all the slow steps. Instead of gradually becoming stars and then a galaxy, the whole thing might collapse all at once into a galaxy, or even straight into a black hole. It's like taking a shortcut through time, jumping ahead to become fully formed in an instant. Another possibility is that the early universe was a very different kind of place than the one we see now. It was much hotter, much more energetic, and full of radiation and wild cosmic storms. Huge amounts of gas might have clumped together quickly under these intense conditions, forming stars and galaxies much faster than today. Think of it as a cosmic wildfire, hot, fierce, and fast-moving, igniting star formation all over the place. And then there's the mystery of dark matter. We can't see dark matter, and it doesn't give off any light, but we know it's there because it has gravity. A lot of scientists now think that dark matter may have acted like a kind of invisible skeleton, pulling in gas and helping galaxies form faster and more easily. If large clouds of dark matter clumped together early on, they could have created the perfect environment for galaxies to grow up quickly around them. But the biggest surprise of all remains those supermassive black holes at the centers of the first galaxies. Usually black holes grow over long stretches of time, feeding on gas and stars getting slowly bigger. But these ancient black holes were already gigantic, in a universe that was only a few 100 million years old. One idea is that they too formed by direct collapse, huge gas clouds collapsing directly into black holes, skipping the star phase entirely. Another theory is that once the black holes formed, they had access to so much gas that they grew incredibly fast, devouring everything around them like cosmic vacuum cleaners. All of these findings have turned old ideas upside down. Scientists used to think that the early universe was quiet and slow-moving, with galaxies forming slowly over time. But now it looks like the early universe may have been much more chaotic, exciting, and full of surprises. Maybe galaxies didn't all follow one simple path. In some parts of the cosmos, they might have grown gently, just as we expected. But in other places, galaxies may have burst into life in the blink of an eye, powered by the intense energy, swirling gas, and the mysterious forces of dark matter. So instead of a cold, dark, and sleepy beginning, the early universe may have been bright, booming, and full of life, with galaxies racing to form, stars lighting up the sky, and black holes growing faster than anyone ever imagined. Even the time once called the Cosmic Dark Ages might not have been so dark after all. It may have been a time of brilliant creation, a wild and fiery chapter in the universe's story when the first galaxies were born with a roar. One of the most exciting and mind-blowing discoveries in the world of modern astronomy, and at the edge of the observable space, is something scientists call the earliest light. This isn't just any light, it's a soft, ancient glow coming from some of the very first galaxies that were born only about 200 million to 300 million years after the Big Bang. Can you believe it? That light has been travelling across space for more than 13 billion years before finally reaching us. It's like getting a glimpse into the very first chapter of the universe's story, a time when everything we know today was just starting to form. Back in those earliest days, the universe wasn't anything like the open starry space we see now. Instead, it was filled with a thick, hot fog made up of tiny particles. This fog was so dense that light couldn't move freely. Light particles, called photons, kept bumping into other particles and scattering in all directions. It was as if the universe was covered by a giant cosmic curtain, blocking any light from shining through. But slowly, over the course of hundreds of thousands of years, the universe began to cool down and expand, and as it expanded, the fog began to thin out. Finally, a moment came when light was able to break free and travel across space for the very first time. This amazing event is known as the Cosmic Microwave Background, or CMB. It's a faint leftover glow that still fills the universe today, like a baby photo of the cosmos, showing us what everything looked like when the universe was still very young. Even more incredible, though, is what happened a little later, between 200 million and 300 million years after the Big Bang. That's when the very first stars and galaxies were born. This was the moment when real starlight first began to shine throughout the universe. And this starlight didn't just brighten things up, it transformed the entire cosmos. Before this time, the universe was dark and foggy, but once the first galaxies and stars came to life, they helped clear away the remaining fog, allowing light to shine freely for the first time. This amazing transformation is called the Cosmic Dawn, the beginning of a new era when the universe lit up with stars, galaxies, and beauty. What makes this discovery so special is that the light from these very first galaxies has been travelling through space for over 13 billion years. That is an unimaginably long journey. And yet, we can still detect this ancient light today. It's like hearing a faint whisper from the dawn of time, a message that carries secrets from when the universe began building itself. This light tells us when stars first formed, when galaxies started to take shape, and how the universe changed from a chaotic cloud of particles into a structured and beautiful place. For a long time, scientists had believed that galaxies started forming this early, but it was very hard to prove. The farther away a galaxy is, the longer it takes for its light to reach us. And since these early galaxies are incredibly far away, their light is also very, very faint by the time it arrives at Earth. To make things even trickier, the universe has been stretching ever since the Big Bang. As space stretches, the light moving through it gets stretched too, shifting from short wavelengths like ultraviolet and visible light into much longer wavelengths, such as infrared, which is invisible to the human eye. To find this ancient, stretched-out light, scientists needed powerful tools. They turned to some of the most advanced telescopes ever built, including NASA's James Webb Space Telescope, the Hubble Space Telescope, and some of the largest ground-based telescopes on Earth. These instruments are specially designed to detect infrared light, which our eyes cannot see but which holds the key to unlocking the secrets of the early universe. One of the biggest challenges in spotting this early light is how much it has changed. Light that was once bright and bluish, like ultraviolet, is now so stretched that it appears red and soft like infrared. That's why infrared telescopes are so important. The James Webb Space Telescope was created specifically to detect this kind of ancient light. With it, scientists can now see things that were hidden before, events that happened just after the universe was born. This ancient light is more than just beautiful, it is incredibly useful. It shows us that galaxies and stars started forming much earlier than anyone expected. This helps answer a major question. How quickly did the universe begin to organize itself after the Big Bang? The answer, thanks to this light, is much faster than we thought. The universe wasted no time in starting to create stars, galaxies, and eventually everything we know. Now let's talk about some of the most mysterious stars of all, known as Population 3 stars. These were the very first stars in the entire universe. They were nothing like the stars we see today. These stars were made almost completely out of hydrogen and helium, the two lightest and simplest elements that were created during the Big Bang. Unlike modern stars, they didn't have any heavy elements like carbon, oxygen, or iron. Because of this, they burned much hotter and lived shorter lives. They shone brilliantly for a brief time before exploding in massive supernovae. These explosions sent energy and newly formed elements flying into space, helping to shape the next generations of stars and galaxies. These early stars also played a key role in a huge cosmic event called reionization. This event helped make the universe transparent, letting light travel freely for the first time. Without these first stars, the fog might never have lifted, and the universe would have stayed dark for much longer. By studying this ancient light, scientists can also figure out how galaxies formed and grew over time. In the beginning, the first galaxies were probably small and oddly shaped, messy compared to the large, beautiful galaxies we see today. But over billions of years, these galaxies collided, merged, and grew larger and more complex. This long process eventually led to galaxies like our own Milky Way. What's even more mind-blowing is that this earliest light connects directly to two of the biggest mysteries in all of science: dark matter and dark energy. These are two invisible forces that make up almost all of the universe, yet we still don't fully understand them. We can't see them, and we can't touch them, but scientists know they exist because of the strange effects they have on everything around them. Dark matter acts like a cosmic glue. It holds galaxies together, using its strong gravity to pull stars and gas into clusters. Dark energy, on the other hand, seems to be the force that's pushing the universe apart faster and faster. These invisible forces are shaping the universe every second, but doing it in secret. Here's where the ancient light becomes especially helpful. Even though dark matter doesn't shine or glow, it still affects how galaxies move and form. The ancient light reveals those movements, like footprints in soft sand. By studying this light, scientists can trace the effects of dark matter and dark energy back to the earliest days of the universe. Every time we find more of this ancient light, it's like peeling back another layer of time. It's as if we're looking through a magical window into the deep past. This light began its journey billions of years ago, before our Earth even existed, before the sun was born. Now, as we observe it, we are watching the universe's first steps, as it grew from chaos into a place filled with stars and galaxies. One of the most breathtaking discoveries so far is the light coming from galaxies that formed only 200 million to 300 million years after the Big Bang. Since the Big Bang happened about 13 billion and 800 million years ago, this means we're seeing light from a time when the universe was still very young, like a newborn. These early galaxies were just beginning to form, and their light has been travelling toward us for nearly the entire age of the universe. And this is only the beginning of what we might discover. Thanks to amazing advances in technology, especially the James Webb Space Telescope, we can now see farther and clearer than ever before. These new tools are opening up parts of the universe that were once completely hidden. With every new bit of ancient light we uncover, we learn more about how galaxies were built, how stars were born, and how the universe slowly changed into the vast, beautiful place we call home. But this journey isn't just about stars and galaxies, it's about us. The more we learn about the early universe, about dark matter, dark energy, and the birth of stars, the more we understand our own beginnings. This ancient light doesn't just tell the story of the cosmos, it helps explain how everything we know, including our planet, our sun, and even life itself, came to be. The universe is packed with strange and puzzling things that continue to amaze scientists and challenge what we think we know. One of the biggest space mysteries is the discovery of black holes at the edge of the cosmos. Immediately after the Big Bang, the universe was a chaotic and extremely hot place, filled with fast-moving particles and powerful light. Everything was growing quickly, and tiny differences in how matter was spread out started to show. Some areas had more stuff packed into them than others, and this uneven spreading led to something incredible. the possible birth of the first black holes, called primordial black holes. These black holes were not like the ones we usually hear about, the kind that form when very large stars run out of energy and collapse. Primordial black holes may have come straight from space itself. They did not come from dying stars. Instead, they were made by the extreme heat and pressure that filled the universe in the very first moments after the Big Bang. At that time, space was not the same everywhere. Some parts had more matter packed into them than others, and gravity pulled these thick areas together. If one of these areas became dense enough, it could crush in on itself and form a black hole, even without a star. These early black holes could have formed just tiny slices of a second after time began, making them some of the oldest things in the whole universe, if they still exist today. Scientists believe that if enough of these very old black holes were made, they could help explain dark matter, the strange, invisible stuff that makes up most of the mass in the universe. Some of these black holes might have disappeared over time because of a process called Hawking radiation, but others, if they were big enough, might still be drifting through space. Even though we cannot see them, they could be pulling on things around them with their strong gravity. Experts think that primordial black holes might have formed during the very first tiny moments after the Big Bang, when the universe was incredibly hot and thick. In those first little slices of a second, small but tightly packed areas of space could have crushed in on themselves because of their own strong gravity, turning into mini black holes. These were not like the huge black holes we now see in the centers of galaxies. Primordial black holes would have been very tiny, maybe no bigger than a single proton. But even though they were so small, they could still hold a huge amount of mass in a tiny space. Some experts think their mass could have ranged from that of a space rock to a chunk the size of a small piece of Earth. If they are still out there, these ancient black holes could be hiding somewhere in the vast universe. Some ideas even suggest they could make up a large part of dark matter, the strange stuff that makes up most of the mass in the universe but cannot be seen with telescopes. Proving they are real could help us learn deep secrets about the early universe and the basic laws that rule everything, like gravity. In the first moments after the Big Bang, the universe was burning hot and tightly packed, filled with wild bursts of energy, light, and tiny particles. Unlike today's big and orderly universe, everything back then was squeezed into a place full of heat and pressure. During that time, matter was not spread out evenly. Some places were thicker than others because of random changes. Most of the time, these small changes balanced out as the universe expanded. But sometimes, a spot was so dense that it could not spread out. Instead, it crushed inward from its own gravity. This crushing led to what scientists now call primordial black holes, tiny but extremely strong objects that may have been around since the start of time. These black holes were not like the ones we usually hear about, which are formed when big stars die and fall in on themselves. The first black holes were born from the wild and extreme conditions of the early universe. Some of them might have been as small as a single atom but packed with huge energy, while others might have gotten larger over time. If they still exist, they might help us understand how the early universe behaved and give us new clues about dark matter. They are called primordial because scientists think they were made during the very first few moments of the universe, long before stars, planets, or galaxies existed. Unlike the black holes that form today from stars dying, these ancient ones might have appeared in the first few seconds or minutes after the Big Bang. During that short but powerful time, the universe was like a boiling sea of energy and particles. If some spots had just the right mix, high pressure and density, gravity could have made them collapse inward and turn into tiny but very heavy black holes. These first black holes might still be out there, hiding somewhere in the huge universe. Some ideas even say they could make up part of dark matter, the invisible stuff that scientists believe makes up most of the matter in space. Primordial black holes are very different from the ones we usually hear about. Most black holes today are made when huge stars use up all their fuel and collapse. These are called stellar black holes, and they can weigh from a few times more than our Sun to many times more. But primordial black holes are thought to have formed in a completely different way, right after the Big Bang in the early seconds of the universe. Because of that, they do not have to be large. In fact, some experts think they could be incredibly tiny, maybe as small as one atom. Even though they are so small, they would still be very heavy, squeezing a lot of mass into a small space. This makes them very interesting to scientists because they might behave differently from the black holes we usually study. Some scientists even believe these tiny but powerful black holes could help us solve some of the biggest space mysteries, like the one about dark matter. Unlike black holes made from dying stars, primordial black holes might have come from the early chaos of the young universe, long before stars even existed. Experts think that just after the Big Bang, small but strong changes in how matter was spread out might have made some areas collapse inward and become black holes. So, primordial black holes did not come from stars. They might have popped into being because of the intense heat and pressure of the early universe. Since they formed so early, these black holes might be much more common than we think. Some scientists believe they are scattered all across the universe, hiding in the vast emptiness of space, maybe even in our own galaxy. Because they are small and do not give off light, they are almost impossible to see directly. But their strong gravity might still give them away. In fact, some scientists think primordial black holes could help explain one of the biggest space puzzles: dark matter, the invisible stuff that makes up about 85% of all the mass in the universe. If this is true, then these old black holes might be the missing piece in the puzzle of how the universe works. At first, primordial black holes might sound like just a strange idea from theory. After all, nobody has seen one with their own eyes, not yet at least. But scientists are working hard to find proof, and there are some exciting clues that suggest these mysterious objects might really exist. One of the most exciting clues comes from something called gravitational waves. These are ripples that move through space and time when huge objects like black holes crash into each other. In the past few years, scientists have picked up these waves using very sensitive tools. Some of the waves they found might have come from primordial black holes that formed in the earliest moments of the universe. If scientists keep finding waves from strange places, it could be strong proof that these ancient black holes are real and still floating out there. Another way scientists look for signs of the early universe is by studying something called the cosmic microwave background, or CMB. This is a soft glow of heat left over from when the universe was born nearly 14 billion years ago. It's like a ghostly light that still fills the universe long after the Big Bang. If tiny black holes formed right after the universe began, they might have disturbed this ancient glow. These changes could leave behind faint patterns, like fingerprints, that today's tools might be able to spot. If scientists find those patterns, it could be another clue that primordial black holes are real. But the mystery goes even deeper. Primordial black holes might also help explain one of the biggest puzzles in science: dark matter. Scientists know dark matter is there because they can see how it affects things, like bending light from faraway galaxies or changing how stars move. But no one has ever seen it directly. That's because it does not give off light, reflect it, or absorb it. It is totally invisible, but it still has gravity, so it pulls on things we can see. If primordial black holes are real, they might actually be dark matter, or at least a big part of it. That would mean they help hold galaxies together and shape how the universe looks. What makes primordial black holes so exciting is that they may have formed before stars, planets, or even light. Today's black holes usually come from massive stars that die and collapse. But primordial black holes could have been born when the universe was still brand new, a hot sea of energy and particles. If that's true, then they are like ancient fossils from the very start of time, silent witnesses to the birth of everything. By studying them, scientists hope to learn what the universe was like when it was just beginning. These black holes might carry secrets about the powerful forces that built stars, galaxies, and planets. They might even teach us about the basic rules that control everything in the universe. And that's not all. Some researchers believe primordial black holes could help solve another deep mystery: what dark matter really is. Right now, dark matter is one of the hardest things to explain. Scientists think it makes up most of the matter in the universe, yet it's completely hidden. If primordial black holes turn out to be part of this dark matter, it could change everything we thought we knew. It would open up new paths in science and help answer questions people have been asking for decades. If these ancient black holes really do exist, they could shake up all of science. They might hold clues that link two of the most important ideas ever made: Einstein's theory of general relativity, which explains how gravity works on big things, and quantum mechanics, which explains how tiny particles behave. These two ideas don't completely agree with each other, and scientists have been looking for a way to connect them. Primordial black holes might be that link. If they help us find the connection, we might finally be closer to a theory of everything, one powerful idea that explains all of how the universe works. Right now, primordial black holes are still one of the greatest space mysteries. Scientists have not yet found solid proof, but the clues are too exciting to ignore. These black holes might be the missing piece in the story of how everything began. It's possible they were made just moments after the Big Bang. They might hold the answers to how galaxies formed, what dark matter really is, and how invisible forces shape the universe. As our tools get better, researchers are getting more hopeful. Step by step, they are getting closer to the truth, trying to find the clues that will show whether these ancient black holes are real and what part they played in building the universe we see today. The universe is unbelievably huge, and even with all we've learned, there is still so much we do not know. Among its many mysteries are these strange and ancient objects, primordial black holes, that may have formed in the very first moments after the Big Bang. They are not just interesting, they might hold the key to one of the most important stories ever told, the story of how the universe came to be. Scientists are eager to explore this exciting frontier, hoping that unlocking the secrets of primordial black holes could change everything we know about the cosmos. When scientists look deep into the wide stretches of space, using the most powerful telescopes ever built, they're not just looking at stars and galaxies far away, they're actually looking back through time. That might sound like something from a science fiction story, but it's a real and amazing part of how light works in our universe. Light doesn't move right away. It travels at a steady speed, about 186,000 miles every single second. That's extremely fast, but space is unbelievably big. Because of this, the light from the farthest galaxies takes millions or even billions of years to reach us. So when we see these faraway galaxies, we're not seeing them as they are today. We're seeing them as they looked a long time ago, sometimes when the universe was still very young. As space scientists study these old galaxies, they've made findings that go against almost everything we thought we understood about how the universe works. One of the most surprising things they found is the presence of supermassive black holes, huge objects with gravity so strong that nothing, not even light, can escape them. What's really shocking is how early in the universe's life these giant black holes seem to have formed. They were around at a time when, according to today's science, they shouldn't have even had enough time to grow. Usually black holes are thought to start small, formed when giant stars run out of fuel and explode in huge blasts called supernovae. These smaller black holes then grow slowly over millions or even billions of years by pulling in gas, dust, and sometimes even whole stars. Over time, they can become truly massive. But in the case of these early galaxies, scientists are finding black holes that were already huge when the universe was still in its first stages, less than 1 billion years old. This is a big mystery. According to our best science, it takes black holes billions of years to grow that large. They need time to pull in huge amounts of matter, and that doesn't happen quickly. Yet these early black holes seem to have skipped all the waiting. They were already massive during a time when galaxies themselves were only just starting to form. Some scientists now think that something strange must have happened in the early universe to let black holes grow much faster than they do now. Others think that maybe these black holes didn't start out small at all. Instead, they might have been born in a totally different way. Maybe from huge clouds of gas collapsing straight into black holes, without forming stars first. This would be a completely different way of being created than what we've believed up until now. Before we look deeper into this puzzle, let's first understand what a supermassive black hole really is. A black hole is a place in space where gravity is so strong that nothing, not even light, which travels faster than anything else, can escape. When something crosses a certain invisible line around a black hole called the event horizon, it is gone forever, pulled in by the black hole's force. Black holes come in different sizes. Some are formed from the collapse of giant stars and are only a few times heavier than our sun. But then there are the giants, the supermassive black holes. These space monsters can be millions or even billions of times heavier than the sun. That's like squeezing a whole galaxy's worth of material into a single unseen point. These huge objects don't just float around in space with no purpose. In fact, they sit right at the centers of galaxies, including our own Milky Way. They act almost like the rulers of their galaxies, quietly but strongly affecting everything around them. scientists now believe that supermassive black holes may actually help shape galaxies, controlling how stars move, where new stars form, and how gas and dust spread out. Sometimes these black holes even shoot out strong beams of energy across space, changing the shape and actions of entire galaxies. In our Milky Way, for example, there's a supermassive black hole called Sagittarius A sitting at the very centre. Even though we can't see it directly, we know it's there because we can watch stars spinning around it at amazing speeds, like leaves caught in a spinning whirlpool. So even though they're dark and can't be seen, black holes are not empty at all. They are powerful engines that have been shaping the universe for billions of years. Some scientists even believe that without them, galaxies might not have formed at all, or at least not in the way they did. To better understand this, let's start from the beginning. Most black holes begin their lives as smaller ones, made when giant stars explode at the end of their lives. The core that's left behind falls in on itself due to its own gravity, creating what's called a stellar mass black hole. From that point, it starts pulling in gas, dust, and anything else nearby, growing bigger over time. Over billions of years, it can turn into a supermassive black hole. But here's the strange part. When scientists look at the farthest parts of space, which means looking back to the very earliest times in the universe, they found something shocking. Fully grown supermassive black holes were already there less than 1 billion years after the Big Bang. That's very early. To explain this, scientists say the universe is about 13.8 billion years old. That means these giant black holes were already huge when the universe was still a baby. This is a big problem for current science ideas. If it takes billions of years to grow a supermassive black hole, then how could one already be so big when the universe was only 700 million years old? It's like finding a full-grown tree in a garden where the seed was only planted a few days ago. Something just doesn't make sense. According to our best ideas, black holes should have formed much later. First, giant stars would need to live their lives, use up their fuel, explode and collapse. Then the black holes made from them would need billions of years to grow, pulling in nearby matter or joining with other black holes. But some of these early black holes seem to have skipped all that. They were already supermassive long before there should have been enough time for that kind of growth. So what could explain this puzzle? Some scientists suggest that in the early universe, black holes may have formed in a totally different way, maybe directly from collapsing clouds of gas, without going through the star stage at all. Others think there might have been black holes that formed in the first few seconds after the Big Bang itself. If these existed, they would have been around since the very start of time, and might help explain how some black holes got so big so quickly. The finding of these early supermassive black holes has thrown scientists into a state of wonder and confusion. It's making us rethink what we thought we knew about how the universe changed over time. Maybe black holes don't always grow slowly. Maybe, in the early days of the universe, some of them were born huge or had a special way to grow fast. No matter which is true, the fact that supermassive black holes were already in the first galaxies, just a few 100 million years after the universe began, is one of the most exciting and puzzling discoveries in modern space science. It's a reminder that even today, with all our advanced tools and smart theories, the universe still holds deep secrets waiting to be uncovered. Black holes grow by pulling in things that are close to them, like gas, dust clouds, and even whole stars. Over time, as they collect more and more of this stuff, they become bigger and heavier. But in the early universe, shortly after the Big Bang, there wasn't much of this stuff floating around yet. The first stars were only just starting to shine, and galaxies were only just beginning to form. The universe back then was still young, quiet, and mostly empty. So here's the big question that has confused scientists. If black holes need to pull in nearby material to grow, how did some of them get so huge so fast, at a time when there wasn't much for them to eat at all? The way we currently think black holes form and grow doesn't explain this. According to our best ideas, it should take a very long time for a black hole to get that big. Yet, scientists have found supermassive black holes, millions or even billions of times heavier than our Sun, that were already around when the universe was only a few 100 million years old. That's just a small part of its current age of nearly 14 billion years. This strange and surprising discovery has made scientists believe that something unusual must have happened in those early days. Either black holes found a way to grow much faster than we ever thought was possible, or there's something big, something important, we still don't understand about how the universe worked back then. To try to explain this puzzle, scientists have come up with several amazing ideas. One idea is that some black holes may have skipped the usual slow growth entirely. Normally, black holes form when very large stars run out of fuel and collapse under their own weight. But in the early universe, there might have been huge clouds of gas, much bigger than anything we see today, that fell straight into black holes without first becoming stars. If this happened, then these black holes would have started out huge, already much bigger than normal ones. That would have given them a big head start in their race to grow even bigger. Another idea is that black holes in the early universe might have been able to grow much faster than they do today. Usually there's a limit to how quickly a black hole can grow. As it pulls in more matter, it starts to shine very brightly from the energy released by that falling material. This light creates pressure, and that pressure pushes back against more matter trying to fall in. This balance is called the Eddington limit, and it puts a limit on how fast black holes can grow, at least under normal conditions. But some scientists think that, in very special cases, black holes in the early universe might have broken that rule. They might have grown so quickly that they went past the Eddington limit, growing at a speed we once thought was impossible. If this is true, it could explain how they became so big in such a short amount of time. There's also another strange idea that goes back to the very beginning of time. Some scientists believe that special kinds of black holes, called primordial black holes, may have formed just moments after the Big Bang, when the universe was still a hot, thick and wild place. These black holes might have formed not from stars, but straight from wild changes in the early universe. If they were born already big, then they would have had a big head start and could have become supermassive black holes much faster than others. It would be like joining a race with a huge lead over everyone else. Yet another idea is that black holes might not have grown all by themselves. Instead, in the early universe, many small black holes could have formed in groups. Over time, these black holes may have been pulled toward each other by gravity and ended up crashing together. These fast crashes could have made bigger and bigger black holes in a very short time, maybe fast enough to create supermassive black holes just a few 100 million years after the Big Bang. But maybe the most mysterious idea of all is that these early giants are trying to show us something even deeper, that we may be missing something very important about how the universe works. Some scientists think that understanding these old supermassive black holes might lead to big new ideas in physics. We might find unknown forces, new kinds of matter, or strange actions that helped black holes grow faster than we thought possible. If any of these ideas are true, it could completely change how we understand the universe. That's why scientists are so excited about the tools they now have to explore the farthest parts of space. One of the strongest tools is the James Webb Space Telescope. Often called JWST, it was sent into space in the year 2021, and it's now looking deep into space and far back in time, taking amazing pictures of some of the oldest galaxies ever seen. By closely studying these ancient galaxies and the black holes at their centers, scientists hope to discover how such huge space objects came to exist so soon after the universe began. To go beyond the part of the universe we can see, people face the huge challenge of understanding the limits of space and time itself. The part of the universe we can see is like a giant dome around us, shaped by how fast light travels and how old the universe is. Beyond this edge are parts of space that we not only can't see, but may never be able to reach. First, let's think about the speed of light. It's the highest speed anything can go in the universe. Nothing can move faster. Since light from faraway galaxies takes billions of years to get to us, we can only see those parts of the universe where the light has had enough time to arrive. To travel beyond this visible area, we would need to either break that speed limit or find a way to bend space itself. One idea that's been suggested is bending space, kind of like folding a piece of paper to bring two far apart points closer together. This idea, often called a warp drive, would in theory let a spaceship squeeze space in front of it and stretch space behind it. That way, it could travel huge distances without breaking the speed limit of light in regular space. Another thing to think about is that our universe is not still. Space is growing, and galaxies are moving away from us. Some areas are moving away so fast that their light will never reach Earth. To get past the edge of what we can see, people may need to build new tools that can detect or reach parts we can't see. Maybe using very advanced machines that can sense changes in gravity or the leftover light from the early universe. Also, we have to deal with the big problems that come with long space trips. This includes systems that keep astronauts alive, shields from harmful space radiation, and making sure the spaceship can survive the stress of such a long trip. Human missions to faraway stars give us just a small idea of what's needed. In the end, going beyond what we can see in the universe needs not only new technology and clever ideas in science, but also a whole new way of thinking about space. It calls us to imagine a future where our drive to explore and create helps us go past what we know today, maybe even finding places and things we never thought were possible. The idea of going faster than light sparks the imagination and brings up some really exciting thoughts. Scientists and thinkers have talked about a few what-if technologies that could make this dream come true. One of the most well-known is the idea of a warp drive. Picture a big bubble surrounding a spaceship. This bubble would bend space by shrinking it in front and stretching it behind. This would let the spaceship ride a wave of bent space, moving faster than light compared to the space outside the bubble, without breaking the rules of physics. Another amazing idea is that of wormholes. These are like tunnels in space and time that could link two faraway places in the universe. If we could make one or keep one stable, then moving from one end to the other might happen almost instantly. But making a wormhole would be very hard. It might need a strange kind of matter with negative energy, something we haven't found or fully understood yet. Some people also talk about using strong magnetic forces to push a spaceship really fast. This idea, called electromagnetic propulsion, is still far from real. But as we improve these systems, we might get closer to making it work. There's also something called time stretching, or time dilation. Even if we can't go faster than light, if we move close to that speed, time would slow down for the travelers. A trip that takes many years could feel short to them. That could help them cover great distances in ways that change how we think about space travel. Even though these ideas are still just theories, they show some of the paths people might take to explore space in ways we're only starting to imagine. Each idea needs more research and big scientific steps forward, but they give us hope for a time when the stars won't seem so far away. Going into parts of space we've never been to is a journey full of both wonder and big problems. One of the biggest is how huge space is. Picture being in a place so big that even if you travel at amazing speeds, it could still take many years, or even hundreds of years to get there. These giant distances make planning a trip very hard. It's not just about choosing the right path, it's also about having enough fuel and supplies for the whole trip. Another big danger is radiation. Out in space, there's a steady stream of harmful energy and tiny fast particles coming from stars, cosmic rays, and other space events. This radiation can hurt people and break parts of the spaceship. Astronauts need strong shields and careful planning, because being around this radiation too long could be very risky for their health. Then there's the problem of low gravity. Even though it sounds fun, living with very weak gravity for a long time can be bad for the body. Muscles get weaker and bones can lose strength. To stay healthy, astronauts need special workouts and diets while they're on long missions. Mental health is also a big concern. Being alone, stuck in a small space, and looking out at the empty darkness of space can make people feel lonely and stressed. On very long trips, keeping astronauts in a good state of mind is just as important as keeping their bodies healthy. Good support systems and fun activities are needed to fight off these emotional problems. Another serious problem is when machines stop working. No matter how high-tech a spaceship is, things can still go wrong. Imagine being far from Earth and having something important break. That's why engineers have to build backups and train astronauts to fix problems fast when things go wrong. Also, unknown places in space come with their own dangers. Things like extreme heat or cold, strange air, or rocky, unexplored land can be very risky. Sudden natural events, like meteor showers or strong bursts from the sun, could be dangerous too, and the crew would need to act fast. The challenges of exploring the parts of space we've never been to are huge. They include finding your way across giant distances, staying healthy, keeping spirits up, fixing problems with technology, and dealing with unknown space dangers. Each challenge needs serious planning to make these space journeys not just possible, but also safe and successful. Wormholes and warp drives are two amazing ideas in science that offer exciting ways to go beyond the limits we have now. Both suggest ways we might skip the huge space between stars and galaxies. Wormholes can be thought of as shortcuts through space and time. If you picture the universe as a flat surface, like a piece of paper, a wormhole would be like punching a hole in it and creating a bridge from one far spot to another. Instead of travelling the whole long way, you could go in one end and come out the other, jumping across space in a moment. But this idea is not simple. A working wormhole would need special conditions like strange matter with very different properties from anything we know so far. Warp drives are another exciting idea. Instead of making a tunnel through space like a wormhole, a warp drive would stretch and squeeze space itself. Imagine the universe as a cloth, and the warp drive makes a ripple in it, pushing the spaceship forward. It squeezes space in front and stretches it behind, letting the spaceship move faster than light without actually going that speed through normal space. But building a warp drive would need super advanced tools, and maybe materials or energy types we haven't discovered yet. Both wormholes and warp drives test the limits of what we know about how the universe works. They make us wonder what else is possible. Scientists are still thinking about these ideas and trying to understand them better, asking big questions about space, time, and how people might someday travel far beyond our solar system. The drive to understand these ideas helps push us forward as we search for ways to leave Earth and explore the stars. Looking for life in places we can't see yet is one of the most exciting parts of space science. As we look beyond our own planet, the huge size of space gives us so many chances to find life in the forms we haven't imagined yet. The universe is unbelievably big, with billions of stars and even more planets. Many of these planets might have the right conditions for life. First, we need to think about life that might be very different from life on Earth. Life here depends on water and carbon, but scientists think there could be life that uses other elements or lives in extreme places. For example, some moons in our solar system, like Europa and Enceladus, might have oceans under their icy surfaces, and those oceans could hold tiny living things. Looking even farther, the discovery of planets outside our solar system, called exoplanets, has made the search for life even more exciting. Some of these planets are in the just right zone, where water could exist as a liquid. If they have air and the right chemicals, they might be able to support life, even if we can't see it yet. Also, the universe is always changing. As it grows, new parts come into view, and with better tools, like stronger telescopes and new space missions, we're getting more information from far-off places all the time. Every time we find things like organic molecules or strange air on faraway worlds, it makes us more hopeful that life is out there. Even though we haven't yet seen life beyond Earth, the chances are big. Every new discovery and our better understanding of how life can survive in different places brings us closer to finding it. Somewhere out there, in the wide, star-filled sky, life might be waiting for us to find it. When we search for life beyond our planet, we're not just trying to answer a scientific question. We're opening a door to the vastness of the universe and asking where we truly fit in. This search invites us to imagine what lies beyond the stars and planets we see, and what it might mean if we are not alone. Scientists who are trying to find life outside Earth often focus on places that might be similar to our world. These are places that might have liquid water, the right mix of important elements like carbon and oxygen, and stable temperatures that don't swing wildly. These ingredients helped life appear and survive on Earth, so they are a good starting point when we look elsewhere. But the search is not only about finding life. It also helps us understand how rare or common life-friendly places might be in the universe. Every time we discover a planet or moon with the right conditions, we get a bit closer to answering the big question: is life a rare miracle, or is it something that happens often when the right pieces fall into place? If one day we do find proof of life, whether it's tiny microbes or complex creatures, it could mean that life naturally arises wherever the environment is right. That would suggest that there could be many worlds in our galaxy, and even in other galaxies, where life is growing, evolving, and maybe even thinking. Each discovery would help scientists better understand the many ways life might survive in strange and surprising environments. It would show us just how creative and flexible life can be, and how wide the universe's imagination might stretch. But what if we search and still find nothing? What if life truly is rare or even unique to Earth? That would also be a powerful discovery. It would push us to look deeper at how life began here, billions of years ago. What were the special conditions that made Earth different? Learning that might help us understand the incredible string of events that led to our own existence, and why it may be so hard to find elsewhere. The search for alien life also forces us to rethink what life even is. We might come across forms of life that are so different from what we know that we don't even recognize them as alive at first. They might not need water, oxygen, or even DNA. Exploring these possibilities makes us think differently about biology, evolution, and what it truly takes for something to live. It stretches our view of the universe and helps us see that it might be far more alive and far more strange than we ever imagined. However, the quest to find life beyond Earth is not just about meeting aliens. It's about understanding the universe, how it works, how it changes over time, and how something as complex as life can appear, survive, and grow. It's about stepping outside our tiny blue planet and trying to see the big picture of existence. Now imagine something even more mind-bending. What if there are alien civilizations out there, far ahead of us in science and technology? These civilizations, if they exist, might know things about the universe that are still completely unknown to us. They might have tools and machines that allow them to explore parts of space we can't even see yet. Perhaps they can detect signals or types of energy that we haven't discovered. They may have been studying the universe for millions of years, collecting information and seeing patterns that we don't yet understand. With a much deeper history and a better grasp of physics, they might already have answers to big mysteries that we're still struggling to figure out. Things like dark matter, dark energy, or how the universe really began. And what if they can travel between stars or even galaxies? If they can move across space the way we travel across oceans, they might be gathering knowledge from distant corners of the cosmos, places we can only dream of reaching. Their discoveries could completely change how we see the universe and ourselves. These alien societies might also see the universe in very different ways, shaped by their own cultures and environments. Their ideas about time, space, or even what it means to be alive might be wildly different from ours. Talking with them could help us look at old questions in new ways and ask new questions we never would have thought of. If we ever did make contact with beings from another world, it could transform everything. Think about it. Meeting a civilization that has been growing and learning for thousands or even millions of years. The things we could learn from them about science, life, even how to live together peacefully, could take us into a new age of discovery. We might meet new kinds of life with strange and wonderful adaptations to their homeworlds. Their biology could be unlike anything we've ever seen, pushing us to rethink how life starts and survives. Their technology might seem like magic to us, but it could inspire our own scientists and engineers to reach new heights. This kind of contact wouldn't just affect science, it would shake up our beliefs, our politics, and the way we think about ourselves. Realizing that we're not alone could make humanity feel more connected, less divided. We might see Earth not as many nations, but as one small world in a much bigger cosmic family. We could also learn new ways of thinking about ethics, cooperation, fairness, and how to build better societies. These beings might have different ways of handling conflict, different ideas about justice, or even how they understand time. Talking to them could open our minds to ways of living we've never imagined. This is why the idea of contact is so powerful. It challenges our knowledge, sparks our imagination, and brings hope that we can grow into something greater than we are now. One of the key efforts in this great search is something called SETI, the Search for Extraterrestrial Intelligence. SETI is like humanity's giant ear, trying to listen across the stars for signals from intelligent life. Imagine standing on a beach, with each wave of the ocean representing a star. Somewhere out there, among the crashing waves, there might be a message. SETI scientists use huge radio telescopes that scan the sky, picking up faint signals from far away. They're listening for patterns or repeated sounds, clues that something intelligent might be trying to say hello. It's like tuning an old radio, trying to find a song hidden among the static. They search across many directions and many types of signals, because any message might be coming from a planet millions or even billions of light years away. And even if it takes centuries to find one, each step brings us closer. SETI doesn't just listen for messages, it also helps us understand where life might exist and how we might talk to it. SETI researchers look at planets outside our solar system, called exoplanets, to figure out which ones might have the right conditions for life. They study how life could exist in all kinds of places, not just like Earth. CT even gets us thinking about what it means to be human. If there are other beings out there, it forces us to reflect on who we are, what makes us special, and how we fit into this grand, star-filled universe. Above all, SETI encourages us to keep wondering, to keep exploring. It reminds us that the universe is vast and full of mystery, and that we are only just beginning to understand it. Maybe one day we'll find someone out there, waiting to share the story of their world. But as we search for life in places no human has ever been, we must be careful. There are important ethical questions we have to think about. For example, what if we accidentally bring Earth microbes to another planet or moon? Even a tiny germ could harm delicate alien environments that have been untouched for billions of years. And what if we find new life or ecosystems, and people try to use them for money or power? Just like we protect natural parks and wildlife on Earth, we must be sure to treat these new discoveries with care and respect. They may hold knowledge that's more valuable than gold, knowledge that could help us understand life, health, or the universe itself. We also need to think about how we act if we meet intelligent life. Do we try to communicate? How do we do it respectfully without causing harm or misunderstanding? If they have societies and cultures of their own, we must be careful not to disturb their natural development. Our reasons for exploring matter too. Are we driven by curiosity and a wish to connect, or by greed and control? Our goals shape the impact of our actions.